Hello, this is Professor Keen, and welcome back to my lectures on electricity, magnetism, and light. In my last lecture, we began discussing the work of André-Marie Ampere, specifically his studies of the relationship between electrical currents and magnetism. That's the overall topic with which Ampere is concerned. We made our way up to about page 83, 84. What I want to do in this lecture is talk about some of his discussion on page 85 and 86, where he talks in more detail about how he's conceiving of the electric tension and the electric current to arise inside of systems like electronic circuits. So if you look down here at page 85, point number 2, he says, let us see, I'm going to read some of this and then comment on it as I go. Let us see in what consists the difference of these entirely different orders of phenomena. He's talking about electric tension and electric current. One of which consists in the tension and attraction or repulsions, which have been long known. So think about when you charge up two small objects, hang them from strings, and then they either attract or repel one another based on whether or not they're both positive, both negative, or opposite charges. And the other is known by the decomposition of water and a great many other substances in the changes in direction of a compass needle and in a sort of attraction and repulsions entirely different from the ordinary electric attractions and repulsions. So there he's talking about the other phenomenon, electric current, and that gives rise to the decomposition of water. We talked about electrolysis in my last lecture, so that's what he's referring to there. The deflection of the compass needle, that's the experiment that Ørsted had done, where you notice that when you hold a compass needle above a current-carrying wire, the compass needle is deflected. So that's indicative of the existence of an electric current. And then he also mentions that is manifested by the attraction and repulsion of, this is what he's going to be talking about next in the next couple of pages, the attraction and repulsion of current-carrying wires. So this is a famous experiment that he carried out, which he'll be talking about shortly. Okay, and now what he's going to do is talk about what the state of electric current consists of and how you generate electric tension. Okay, so he says, I believe I first discovered this, that's the attraction and repulsion of current-carrying wires, and which I've named voltaic attractions and repulsions to distinguish them from the other types of attractions and repulsions. Okay. Now, he mentions that when there is not conducting continuity from one of the bodies or system of bodies in which the electromotive action develops to the other, and when these bodies are themselves conductors, as in Volta's pile, we can only conceive this action as constantly carrying positive electricity into the one body and negative electricity into the other. So imagine a situation where you have a battery. Let me draw a battery right here with a positive terminal. This is a voltaic battery. If it helps you, just think about a car battery. And let's suppose this is a 12-volt battery. What that means is that there's a potential difference of 12 volts. Remember, potential difference is measured in volts. So sometimes we'll call potential difference voltage. So that's the difference in electric potential between these two terminals. Now let's suppose you have a conducting body like a spherical ball, and let's suppose that this is put on top of an insulating rod. Okay, and let's suppose you have another spherical conducting ball right here on top of another insulating rod. So these are two metal spheres atop, let's say they're atop plastic rods, which of course are insulating. And let's suppose you hook up one of these to the positive terminal of the battery. You make a connection right here, and the other one you hook up to the negative terminal of the battery. So what happens, he says, when you do this, the positive charge, the positive electricity, is going to move from the positive terminal of the battery and build up on this metal sphere. So this sphere will become positively charged. And likewise, the negative electricity flows from this terminal and builds up on this sphere. That's how he's considering this. Okay, he says the two electricities accumulate each in the part of the whole system to which it is carried but this effect is checked as soon as the difference of electric tensions give to their mutual attraction, which tends to reunite them, a force sufficient to make equilibrium with the electromotive action. So he mentions this electromotive action, or sometimes electromotive force. The battery is producing an electromotive force by virtue of its voltage. That electromotive force is, as the name might suggest, trying to move electricity. So it's pushing positive electricity onto this ball, and it does so up until there's equilibrium reached. In that case, when this left sphere gets to be a high enough voltage that no more, eventually what happens is this electrical current stops flowing from the battery over to the positively charged sphere. So let's suppose that this is at plus 6 volts and this is at minus 6 volts. I'm just using an example, plus 6 and minus 6. So when this sphere right here gets to a voltage of plus 6 volts, then there's equilibrium on this left half of the circuit, and no more positive charge will flow onto the sphere. And likewise, when the right sphere gets to negative 6 volts, because there's enough negative electricity built up on it, then there will be equilibrium established on the right side of the circuit, and so there will be no more electrical charge flowing onto the left sphere. So you can think of a voltage difference. Originally, this left sphere was at 0 volts. This was at the left side of the terminal was at 6 volts, and electricity flows over here until the voltage is equilibrated on the left side. So a voltage difference between the terminal of the battery and the left sphere drives the flow of electrical current. It's a bit like when you have a temperature difference driving the flow of heat. So if one object is at 50 degrees Celsius and it's in contact with another object that is at 20 degrees Celsius, there will be heat flow until they arrive at the same temperature. Likewise, in electrical circuits, when there's a voltage difference between 2 points in the circuit, there will be electrical flow of electricity until the voltage arrives at a uniform voltage in that part of the circuit. Now he goes on to say, then everything remains in this state except for the leakage of electricity, which may take place little by little across the non-conducting body, the air, for example, which interrupts the circuit. For it appears that there are no bodies which are perfect insulators. So notice that these two spheres are separated by air, and although you'd hope that air would be perfectly insulating, it's not. And so what happens is the positive electricity leaks across the air into the negatively charged sphere, and likewise negative electricity leaks across the air over to the positively charged sphere, but it happens at a very slow rate, and as it does that, the voltage on the left sphere goes down and the voltage on the right sphere goes up. I guess it gets closer to 0. And when this happens, if the leakage is slow enough, well then the battery is able to replenish the charge very quickly, and it keeps it up very close, the left sphere very close to plus 6 volts, and the right sphere very close to negative 6 volts. So the electromotive action or force that's driving electricity from the positive terminal of the battery is able to replenish this charge very quickly. Okay, so he says, as this leakage takes place, the tension diminishes, but since when it diminishes, the mutual attraction of the two electricities no longer makes equilibrium with the electromotive action, this last force, in case it is constant, carries new positive electricity on one side and negative electricity on the other, and the tensions are reestablished. It is this state of a system of electromotive and conducting bodies that I called electric tension. Okay, so this is just kind of a more detailed look at how the state of electric tension between these two metal spheres is established. Okay, now let's go on to the next page. On the next page, 86, he in the top paragraph, or I guess the long paragraph, now he's going to talk about what happens when you connect those two spheres by a conducting wire. Okay, he says, when the two bodies, or the two systems of bodies between which the electromotive action arises, are also connected by conducting bodies in which there is no other electromotive action equal and opposite to the first, which would maintain the state of electrical equilibrium, and consequently the tensions which arise from or result from it, these tensions would disappear, or at least would become very small, and the phenomena occur which have been pointed out as characterizing this second case. Okay, so what he's saying here is, let's suppose you take a wire now. Let me imagine you take a copper wire and you connect it between these two spheres. So you connect with a conducting wire like copper. And what happens now is you get a flow of positive electricity very quickly over to this side and negative electricity very quickly over to that side, so as to try to relieve this electric tension. That is the state of electric current. So now you get an electric current that arises in this circuit. Okay? That's what he's talking about. What might have been a little bit confusing in the top of the paragraph, he mentions if you connect them but with something that generates an electromotive action or force that tries to prevent flow. So if you were to put another battery in here instead with the positive terminal on the left and the negative terminal on the right, that pushes positive charges back onto this sphere and negative charges back onto that sphere, then you wouldn't get any flow of electricity between the two. But if you just connect them with a conducting wire, then you're going to get this electric current arising. Okay, he says, but as nothing is otherwise changed in the arrangement of the bodies between which the electromotive action develops, it cannot be doubted that it continues to act, and as the mutual attraction of the two electricities, measured by the difference in electric tensions, which has become nothing, or has considerably diminished, can no longer make equilibrium with this action. It is generally admitted that it continues to carry the two electricities in the two senses in which it carried them before, in such a way that there results a double current, one of positive electricity, the other of negative electricity, starting out in opposite senses from the points where the electromotive action arises and going out to reunite in the parts of the circuit remote from these points. Okay, so there he's simply saying that you have this flow of electricities from the positive to the negative sphere and from the negative to the positive sphere. Okay, now he says something else in here. There's a couple of sentences where he conceives of how this electricity moves. Does it move instantaneously or does it have to accelerate? He says the currents of which I am speaking are accelerated until the inertia of the electric fluids and the resistance which they encounter because of the imperfections of even the best conductors make equilibrium with the electromotive force, after which they continue indefinitely with constant velocity so long as this force has the same intensity. But they always cease on the instant that the circuit is broken. What is he talking about here? He says, well, you've got this electromotive force, this voltage difference between the positive and the negative spheres, and that electromotive force is going to try to drive these the electric fluid between the spheres. Just like you might think about with the force of gravity. If you drop something off of a balcony, the force of gravity tries to accelerate that ball toward the ground. So there's an acceleration of the ball toward the ground, and similarly he's saying there's an acceleration of this electric fluid from the positive to the negative sphere, and likewise from the negative to the positive sphere. And does this just keep accelerating it, getting faster and faster and faster? He says no. Eventually what happens is there's some resistance that arises even in the best conducting bodies, which prevents it from accelerating to an infinite speed. This is really analogous to the idea of a terminal velocity. So if, for example, you were to drop a ball off of a building, a very tall building, what would happen to its speed? Well, if this is the speed, I'll make a diagram down here, as a function of time. This is for a falling ball. Well, what happens is at first the speed starts increasing more and more and more and more. But as it gets faster and faster, what happens is there's a drag force that acts between the ball and the air, and that checks the rate of increase of speed. And in fact, at some point in time, the speed becomes constant when the drag force is exactly balanced by the force of gravity. And it is at that point that the ball is said to have achieved terminal velocity. The final velocity that that a falling object will acquire. Of course, it's going to depend on the shape of the ball. If this isn't a ball, it's a very sharp missile or something like that, then it's going to have a very high terminal velocity. A parachute has a very low terminal velocity. Okay, but in any case, you've got this initial acceleration, and then the acceleration is reduced, and eventually the acceleration goes to 0 as it achieves a constant speed. That is how Ampere is imagining the current behaving in this circuit. There's an electromotive force that accelerates the current until eventually there is some drag exerted by the conducting wire on the fluid that is trying to accelerate through it. At that point, it experiences a constant electrical current. Okay, and now finally, what does he say in these last couple of sentences here in this paragraph, or I guess the last 1/3 of the paragraph? He talks about the sense of the electric current. What does he mean by the sense of the electric current? Okay, so let me come back over here and talk about the sense of the electric current. Okay, this problem might have come to your mind as I was talking. We're talking about there's a current of positive electricity going in this direction and a current of negative electricity going in this direction. But when we talk about an electric current, which of those are we referring to? Are we referring to the positive flow or the negative flow? And Ampere says, well, let's just adopt a convention. We're going to adopt the convention that whatever way the positive electricity is flowing is what we are going to call the electric current. The sense of electric current, he says, is, by convention that he is adopting, the direction of flow of the positive electricity. So we would say, and this is the convention that is adopted to this day, we would say that in this circuit there's a current flowing around in this case it would be in the clockwise direction. Okay, so let me make this orange to highlight it. There's an electrical current flowing in this circuit in the direction of the positive electricity. We say that there's a clockwise current flowing through this circuit. In reality, we don't know at this point which is really flowing, or if both are flowing. Is it the positive charges that are moving this way? Is it the negative charges that are moving this way? Or is it both positives going this way and negatives going this way? Well, he says it doesn't matter. We'll just talk about the direction positive charges are going and call that the direction of the electric current. Okay? All right. And remember, there are, I guess maybe I'll say one other thing about that. When you have some situations you set up, there are positive and negative electricities in fact flowing. So if you have a battery hooked up to a saltwater bath, so I mentioned this in my last lecture. So if you have a battery hooked up to water, and to emphasize this, let's make this salt water. So you've got sodium and chlorine ions that are dissociated in this. Well, in that case, you're going to have if this is the positive terminal of the battery, oops, let me go back. If this is the positive terminal of the battery over here and the negative terminal of the battery over here, you will have the positive sodium ions moving in that direction, and you'll have the negative chlorine ions moving in that direction. So you do have both positive ions moving that way and negative ions moving that way. Okay, so in that case, we still would call this a current in this direction, because by convention, he says the current is flowing in the direction that the positive charges are moving.